we were talking about dictionaries and how, like, when we were doing that linear search, for example, if we had a list of sublists, and the sublists are just pairs of names and grades, we saw that, you know, if there's n students and we're looking for a specific student, it's just a linear search. We got to go through and search, and if there's n of them, it's going to take like n units of work to get that done. And if we double the size of n, it's double the amount of work. But we also saw how we could take advantage of a dictionary to do kind of this same idea, but we make the keys the student names and the values their grades. And suddenly I was telling you that, like, oh, it's so much faster, which it is. And we very briefly talked about the hash function and whatnot and how it's magical. And we also talked about how, well, you've seen other things in Python that are like shorthands for doing linear search, but I was saying how, well, in the back it's still got to do linear search. But dictionaries don't. Asterisk. You'll learn all about these asterisks later. So they're awesome. If there's n students, it's one thing. It's like, okay, well, dictionary, key of the student name, it just tells me, boom. If there's n students, it takes 1 unit of work. If there's 2 times n students, it's still 1 unit of work. That's awesome. We call that like constant time. If you have an algorithm that, regardless of the input size, always runs at the same speed every single time, you're in great shape. We love that. But that doesn't happen very often. Okay, here's what I want. This activity, but, and I'm going to warn you, this is a tricky one. I'm not expecting you to actually get this done, and I'm not going to go over the solution of this one. This right here is one of the classic, quintessential, introductory programming problems. And the reason is, at this stage, here I'm saying, okay, given an array or a list of integers, return the indices of 2 numbers such that they add up to a specific target. You may assume that each input would have exactly one solution, and you may not use the same element twice. So there we go. If the list is 2, 7, 11, and 15, I'm looking for 9, well, the sum of 0 and 1, like the indices 0s and 1, is 9. Therefore, I return 0 and 1. Wonderful. It's not difficult to come up with the solution to this problem, but it becomes a lot more difficult to come up with a good solution to this problem. So what I want to do is I want to give you at least 5 minutes of time to solve this problem. Okay? But at this stage, don't think about dictionaries. Ignore dictionaries. You've got a list. And you got to go through and see if you can find any pair that adds up to a specific number. So what I'll do is I'm going to start like writing the function, and then I'll hand it off to you, and I'm going to give you a chunk of time to try this one, because this is a good problem. There. So assume we get some list of whatever size, and we're looking for a specific target. I'm going to give you a good chunk of time for this, so have fun. Feel free to chat amongst yourselves if you get stuck or something, but go for it. If you're having a hard time getting started, if you're at it, keep at it. But if you're having a hard time getting started, it's always good to think, if I told you, a human, not a computer, if I told you, a human, to do this, what are the steps you would do? And think of the most atomic, basic steps that you're doing. As silly as it feels, do that, because usually code is those simple, tiny little bits of steps. I'm going to give you another hint if you're stuck. You're going to have, and listen carefully, you're going to have at least one linear search. At least one. Does anyone have it? 1, 2, not many people. That's okay. This is probably by far one of the more challenging things I've asked you to do so far in the class. I realize, sometimes the assignment looks like complex, but really half the challenge of the assignment is understanding what the requirements are. This one has a simple requirement, but it's a tricky problem to solve. It's easier to solve it one way than another, but let's take a second and think about this. I need to find if any pair of numbers in that list add up to a certain value. And the first hint I gave you is, well, what would you do? How do you do this? And I don't know about you, but this is how I would do it. First, I start by going, okay, 1. Does 1 plus 5 equal, in my case, I'm looking for 12. Does 1 plus 5 equal 12? Answer me. Try harder and answer me. No, or false. How about 1 and 8? 1 and 2? 1 and 4? Huh. So I know 1 must not be in that pair, right? So what about 5 and 8? Come on, you can count. 5 and 2? 5 and 4? No? So, okay, let's go on to 8. How about 8 and 2? I mean, there's no sense in checking 8 and 1, because we already did that when we checked 1, right? Because we checked 1 and 8. If 1 and 8 isn't, 8 and 1 isn't. So we can kind of just move our way down. But 8 and 2, no. How about 8 and 4? Hey, we're in great shape. So what was I doing there? Well, I started one number, and then I looked at all the remaining numbers. Then I went to the next number and looked at all the remaining numbers for that number, and so on and so on and so on. Let's think. Okay, so first things first. If I want to go through and go here, and then here, and then here, and then here, and then here, I mean, that's easy. That's just a loop. Let's make sure I can get that working. For I in range len of a list. Let's print out I and A at I just to see what happens. 0, 1, 1, 5, 8, or 2, 8, 3, 2, 4, 4. Good, that checks out. The loop's going through, it's telling me what the index is and the value. Index value, and so on. Great. So that's like only half the problem though, right? Like that's great. I put my finger on each value in there, but I don't want to just print it out. I got to do something with it. So when I go to 1, I need to loop through the remaining list for 1, right? Here's where things get a little tricky. We can make this slightly better in a moment. I put a loop inside a loop. Here's my thinking. I need the outside loop to go, okay, 1, 5, 8, 2, 4. But when the outside loop runs the first time, its index, like I is going to be 0, and the value is going to be 1. But then I need to run that inside loop to go over all the values in that list. To see if, okay, I'm starting at 1. Now go through the rest of the list, see if anything adds up. Yes, no, if go to the next one. Then another loop to go through and so on. Go to the next one, but we got to run that inside loop again. So the outside loop is kind of the okay, 1, 5. The inside loop is, okay, we've got 1, now check these things. Then the outside loop goes. Then the inside loop runs. Now, as I have it written, I can improve this a little bit. Let's start at I. Actually, I can start at I plus 1. Because otherwise, the inside loop would always start at 0, which isn't horrible, I suppose, but we can improve it because, as we saw, like, we're never going to want to sum 1 and 1. We can only ever sum 1 and then whatever comes after. So that's why I can start the inside loop at I plus 1. And the next time through the loop, it'll be here. I is 1. Well, we can start the inside loop at I plus 1. We just shaved off a couple units of work. So I've got a loop inside a loop. This is weird. Are there any questions so far? Because now is really a good time to ask. Yes?
I deleted, like, I searched through and, like, made a new list, like, that would get rid of any integer, like, above the target. Would that work?
Did it?
Like, it seemed to. I didn't finish everything else, but...
All right. Well, keep working at it, and then you tell us.
All right.
Here's what I'm going to do. I'm going to print I and then J. Do that, and then out here, print just whatever. Okay. So here's what I'm going to do. Each time the inside loop runs, I'm going to print out I and J. And I'm not going to add, actually I should probably do like here's what I'm going to do. And this end equals nothing. That's a way to say, like, don't print a new line at the end of the print. And then once that inside loop finishes running, this is just going to print out a line for us. And I'm going to hit run. Look at that. What does this mean here? Well, first it's saying 0, 1. Then 0, 2, 0, 3, 0, 4, right? Then the next time the outside loop runs, we're at 1. So then we see 1, 2, 1, 3, 1, 4. Then the outside loop goes again. 2, 3, 2, 4. And so on. How many times the inside loop runs 1, 2, 3, 4 times during the first time the outside loop is running, right? How do I know? Well, I mean, I can count right there. So that inside loop runs 4 times when I is 0. Then it runs 3 times when I is 1. Then it runs 2 times when I is 2. In total, the inside loop is running 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 times. The outside loop runs 4 times. Why? Well, 1, 2, 3, 4. For the fun of it, I'm going to get rid of this just to see how it changes it. There. Now we print out the whole square. 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, and so on. Are there any questions about this? So do we see how the inside loop is going to run however many times each time the outside loop runs? Cool. Now I'm going to add that fancy math back. There. So here we go. Now, I don't want to print anything out. I want to ask a question. If a list at I plus a list at j is equal to target, well then we found it. Return what did I say? ij. Great. If we ever exit that loop, I guess return nothing. I'm returning tuples because why not? Return nothing because there is nothing that adds up. Let's see if it works. I guess I have to print result. 2, 4. 0, 1, 2, 3, 4. 8 and 4. Aha! Awesome. So here's a working solution. It required a loop inside a loop because we were doing like a linear search for every linear search. Here's what I mean. For each number, I had to do a linear search. I go to the next number, do another linear search. Go to the next number, do another linear search. Next number, another linear search. Questions, because now I'm going to start getting us to think a little bit more like a computer scientist. So please ask the questions right now if you got them. Yeah?
That return under the first four or the second one?
This one? Or this one?
Yeah, no.
This one, it's outside the outside for. It's, yeah. Other questions? If the return was inside the first for loop, the first for loop would only ever run once. And that's no good. Yeah?
Is it better to use a for loop and then instead of like a while loop?
It doesn't really matter in this case. They're both doing the same thing. Use whatever you like better. Like I could have replaced those fors with a while. Doesn't matter. All right, so I got a question for you. We're going to hit pause on this. I know I sound like a broken record. If I said, here's the algorithm for a linear search, start at the beginning, go to the end, and find something. If I had a list of size 10, how many times is that loop going to run? Yell it. 10. Come on. Wake up. 10. What if it was size 20? 20. What if it was size n? N. What if it was 2 times n? 2 times n. Great. That's how much work a linear search is taking. Now let's look back at this code. And you know what? For simplicity, I'm going to get rid of this. Because it'll still work. We're just doing a little bit extra work. So now I'm not doing the fancy half a square, I'm doing the full square. It's going to be a little easier to think about that. Think about it, how much work is being done if we're doing all that. The code still works, still gives me the result. Here, I'm also going to go back, and for the fun of it, print and I suppose what I'll do is this. Res equals I, j, and then down here I'll just return res. Effectively the same thing, but I'll only return at the end of the function. There's only one return. I just changed it a little bit. Okay, great. Oops, what did I do? That's unusual. The last one makes sense. It should have had no new line here. Oh, you know why? There we go. Much better. Okay, great. How How long was this list? 4. How many times did a loop run, though, in this function? I lied, the list is length 5, not 4. How many times did that loop run? Or not that, how many times did how many loops ran? I gotta make sure I'm wording that correctly so we don't get confused. How many times did some loop, run? Yell out the answer. 25. Why did you word it like it was a question?
I'm not sure.
25. Why? Well, I can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. I can count those things. But also, how many times is the outside loop going to run? You got to know the answer to this. 5. For each one of those 5 things, how many times will the inside loop run? 5. So we are going to run the inside loop 5 times for every single time the outside loop runs, which is running 5 times. If you do something that takes 5 units of work 5 times, how much work do you have? 25. Interesting. How much work do you think there would be if I made the size of the input not 5 but 6?
36.
What if I made it 7?
49.
What if we had more than just you answer questions? What if it was 10? How much work? 100. So, maybe you're starting to see a pattern, right? If I gave you something of size n, where n is some arbitrary number, how much work will this function do? N squared. Interesting. Which would then mean, if I doubled the size of n, how much more work is there? 4 times. We didn't double the amount of work like we did with the linear search. With a linear search, if we doubled the input, we did twice as much work. But with something that looks like this, if we double the input, it's a lot more than just double the amount of work. This grows at a rate of the amount of work done grows proportional to the input with that squared relationship. Something like this is going to take a lot longer to run than something that's linear. Something that's just if you double the work, it doubles, or double the input, you double the work. This is going to be a lot slower. Now, if we go back to that activity, we call this the computational complexity. How much work is being done in this algorithm? How much work do we have to do as the input size grows? All these fancy questions computer scientists like to ask. But here, what we have right here is the solution to that activity I gave you that has a solution. This code is it's n squared. It's quadratic. There is a solution, though, to this problem that is linear. There is a solution to this problem that if you double the input, it only doubles the amount of work. And that's what makes this activity tricky. We're not going to do it right now, but I strongly, strongly, strongly encourage you to try to figure this out. It's a classic problem. If you get really stuck and you Google the solution, you'll find it, but please don't do that. You'll spoil the fun. Any questions about that? So we just got a view of a very critical, important computer science idea that, well, you know, some algorithms, the amount of work they're doing only grows linearly, and sometimes it can grow with that like quadratic relationship. We like things that take less time to run. We don't want runtimes to take a long time. There are a lot of examples of problems out there that can become so computationally expensive that it's prohibitive to even run the code to solve them. And let's talk about a quick example right now. Has anyone in here, raise your hand if you have, I'm not actually expecting anyone to raise their hand, but raise your hand if you have heard of the question or the problem, the traveling salesman problem. No one's heard of it. Okay, that's good. Well, not good, but okay. So here's the problem. It's very easy to understand. You are a salesperson, okay? And you live in Antigonish. So here you are. Your home is here. Great. I don't know how hard this is to see at the back, but hopefully you can manage. So here you are in Antigonish. And your job is that you need to go out and start selling stuff. First, well, actually, I shouldn't say first. And you have to hit some number of cities. Maybe you have to hit like New Glasgow, Port Hawkesbury, Guysborough, I don't know, Truro, Halifax, and I don't know, some other places in between. Okay? You can get from any city, like you can get to all the cities. You know, there's roads, you know? Maybe there's like the road from here to here, maybe there's one to there. I'm just drawing, like, pretend these are roads. I don't know, you can get from anywhere to anywhere, basically. I'm missing a lot of stuff. Maybe, I don't know, there's a big road there. Who knows, whatever. So here's the goal. Assume everything's connected to everything. Here's the goal. You have to start in Antigonish at home. You have to hit every single one of these cities, towns, whatever, and end in Antigonish. So you need to start and end in the same city. You have to make sure you hit every single one of these cities. I know I only drew some number of roads. Pretend everything's connected to everything. And you need to hit every city. But you want to minimize the total amount traveled. So, I mean, you as a human, you're going to say, well, it wouldn't make a lot of sense. I don't know, maybe we got Sydney up here too. It wouldn't make a lot of sense to go from like Antigonish, New Glasgow, Port Hawkesbury, Truro, Sydney. Like, that would be way too much. We're wasting a lot of time. We're doubling back far too often. So the goal is to come up with some minimal path. We call this fancy path a Hamiltonian cycle. And I don't know, maybe it looks something like this. And I don't pretend there's a road there. Great. That's probably the correct solution, right? I just eyeballed it. Now I have a question for you. How many possible combinations of, like, how many orderings of cities are there? Take a second and think of it. How many cities we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Great. Don't answer. Let's work this out. So we have to start, we have 11. We have to start in Antigonish. If we start in Antigonish, how many options do I have? I have 10, right? Okay, great. Then, so let's say I pick one of those options, New Glasgow. It doesn't really matter which one I take, but after I go to that first city, how many options do I now have? 9. Then how many do I have? 8. Then 7, then 6, then 5, then 4, 3, 2, 1. So, who remembers what like 10 times 9 times 8 times 7, dot, dot, dot. What do we call this? An integral? Factorial. I only briefly talked about that, so if you don't remember, that's fine. But a factorial, sometimes we write that as like 11 exclamation point. 11 exclamation point means 11 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, of course, because we know we're starting in Antigonish, it's only going to be 10, because I have 10 options and then 9 options and then 8 and 7 and 6 and so on. But that's how many different combinations, that's how many different orderings of cities there are. That seems like a lot, doesn't it? Only 10. And that's how many orderings there are. I suppose technically a path that is a reverse of another path, we can ignore that, I guess, because it's effectively the same path. So if we want to get fancy, I suppose we can divide that by 2. Because going this way or going this way, it's the same. So if we want to get fancy, I suppose we could take that. Whoop. Divided by 2. Great. There. That's how many there are. Why do I care about how many there are? Well, if I were to write a program to find the optimal solution, here it is. This is the simplest program. It is so easy to find the solution to this problem. The code to find the best solution possible for the traveling salesman problem is so easy to write. Here's what you do. Generate every single possible ordering. Calculate the total distance. And then pick the one that's the shortest. Raise your hand if you agree. Yeah, that'll work. I mean, yeah, obviously. You just calculate all of them. Pick the minimum. Done. Easy. Really easy. That's like a couple lines of code, no problem. Now, if I gave you a list and I wanted you to do a linear search, and the list had 10 things, how many things do you have to look at? 10. If I gave you something with 100, you only have to look at 100 things. But now we're in a sticky situation. Here we had 11 cities. And we had to look at 1,814,400 different orderings. I wonder how many orderings there would be if, oh my goodness. That's 100 cities. And we have times 10 to the 157. 100 cities. If you had to do a linear search on 100 things to find, like, oh, the student in the class, you only have to look at 100 things. But if I gave you 100 cities and told you to solve this problem, it would have to go through 4.666311 times 10 to the 157. You know what's weird? How many items are, how many hydrogen atoms are there in the universe? Just one sec. Hydrogen is like the most abundant thing in the universe. So I wonder how many hydrogen atoms there are, approximately. 5, given the estimate 5 trillion hydrogen, oh wait, I'm going to switch this around. Because I know this will give me, it looks like there would be a 10 to the 78, 82 atoms. There are more combinations of 100 cities than there are particles in the universe. Who here thinks that's messed up? I think it's messed up. You could take every single particle in the universe and assign it one of the unique orderings, and you would run out of atoms. What was your question?
I think I figured it out, but it's also kind of not really related. It's going, never mind, we're good.
All right.
Yeah.
What were you going to say?
I was going to say, with the code we were doing before, with the linear searches, with the one inside the other, when we had 5 of them, there was only like a maximum of 25, but really we could get that down to 5 plus 4 plus 3, blah, 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 blah. Whereas 5 factorial is like 120 or something. So it wouldn't be factorial, it would just be like adding one.
I think you're trying to connect dots that we shouldn't be.
That's what I mean. That's why I was
All
saying,
right.
never mind.
We can talk about it later. So, why is this a problem? Well, let's say I've got the world's fastest supercomputer. Okay? And let's say the world's fastest supercomputer can evaluate a trillion things a second. So let's say, for fun, this computer can look at 1 trillion orderings in 1 second. Okay? So if I go back to here, I'm going to take this value. Okay? Whoop. I'm going to divide that by 1 trillion. Okay, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. I think that's a trillion. That's how many seconds it would take. You know what? For fun, let's make it like a quadrillion. Or what's 5?
Or no, what?
Whatever. That's a really fast computer. If I had that, that's how many seconds it would take. Okay. How many seconds in a minute? So I can divide that by 60. That's how many minutes. There's 60 minutes in an hour. That's how many hours. Divide by 24 hours in a day. Divide that by 365 years. Oh my goodness. It would still take like times 10 to the 116 years to solve. How long has the universe existed?
Less than that.
A hell of a lot less than this value. Here we have a problem that grows by like a factorial. So we saw one linear, great. When we talked about using a dictionary, suddenly it made everything constant time. No matter how big the input is, it's always like 1 unit of work. We saw linear, we saw quadratic. And here's an example of something that if you do what we call a brute force search, which is absolutely guaranteed to give you the optimal solution, that grows proportional to n factorial. We can get fancy and say n minus 1 factorial divided by 2, but it's going to be proportional to n factorial. And if you combined all the computing power that humanity has, it would take orders of magnitude longer than the universe has existed to go through each of those combinations of 100 cities. So we have a very simple algorithm to find us the best possible solution. Is it feasible? No. I mean, that's not going to happen, is it? How about that? All right, we'll end there.